Good afternoon, everyone, and welcome to Wausau Distance Education. This is MBF3C, grade 11 work college preparation mathematics, and my name is Marvin. Welcome to the 18th class of the semester. Today is October the 2nd. We had a very nice day yesterday. Yesterday we started looking at annuities. So we worked through some problems where we had to use the present value and the monthly payment if we were to borrow money. So an annuity would be, when you get a bank loan, for example, and you have to make monthly payments. So when we talked about simple interest and compound interest, we looked at problems where we just calculated how much will be owed at the end of a period or how much interest we would have to pay at the end of a period. But that was if we just borrowed money and at the end of the period we paid it all off at the same time. That's not how it usually works, though. Usually we have to make monthly payments. So if you buy a vehicle, for example, you don't have it for 3 years and then go in and pay off the amount you borrowed. You make monthly payments. So that's what we're getting into when we talk about annuities. So we worked on a couple of problems yesterday, and we're going to work on another one today, and then we'll move on from there. So let's go to scroll back up. So right here you can see the R formula being used. So here we were calculating the amount of the monthly payments we would have to make if we borrowed $24,000. Putting money down, like $1,000 down. The first one we looked at was we didn't know how much we were going to borrow, but we knew how much we were going to pay and for how long, and then from there we could figure out how much we were going to borrow. So two different problems. We're going to take a look at another one that's slightly different so that you have various examples to follow when you start working through the support questions and the key questions. Again, support questions you don't submit for marking, only need to submit the key questions. But it's important that you work through the support questions before you do the key questions to make sure you understand the concepts and you're able to do the problem. If you're having trouble with the support questions, you can call me and we can work on them together, whereas I can't do that with the key questions. But if you can do all of the support questions, and the key questions are very similar, so if you can do the support questions, you should have no issue with the key questions. So let's take a look at a problem. It says, due to their credit ratings, Brett can borrow money at 8.5% compounded monthly, but Glenda must pay 12.1% compounded monthly. So again, as I talked a little bit about this yesterday, you have a credit score. So based on your credit history, which means, you know, previous loans, making payments on your credit cards, paying all of your bills on time. If you do all of that, then you have a good credit score. But if you don't, and you have a lower credit score, then they're probably going to charge you a higher interest rate. And then you're going to pay more. So Brent's got to pay 8.5% per year compound annual, and then Glenda has to pay 12.1. So she's paying close to 4% more in interest than Brett. So, how much more interest would Glenda pay than Brett on a $14,000 loan with monthly payments of 4 years? So monthly payments again, that means 12 months, 12 payments per year. So we know that the present value we're starting with is going to be $14,000. Okay, so we'll highlight that. Present value in each case, they're both going to borrow the same amount of money. N is the number of interest periods per in total. So we're going 4 years, okay, 4 years and compounded monthly. So 4 years compounded monthly is going to be 12 times 4 or 4 times 12, which is 28. And the interest rate, so for Brett and for Glenda, those two numbers are going to be the same. Where it differs is the interest rate. So the interest rate is interest rate per period. For Brett, it's going to be 8.5%, which is 0.085. So take the 8.5, divide that by 100, and you'll get 0.085 divided by 12. We're going to leave that as a fraction, otherwise we're going to get a funky number. So we'll leave it as a fraction for now. Glenda's interest rate is going to be 12.1% or 0.121. So divide that by 100 and then divide that by 12 because we're compounded monthly. So we're dividing it by 12. The next part, again, we have our givens. So now the solution, uh, slash, the solution, let's underline this as well, I guess. Oh, we don't need to, I guess. Yeah, we better. So the solution is going to be first the formula for each of the two individuals. So for Brett, we're looking for the monthly payments. How much is he going to pay per month? So it's going to be a formula PVI divided by 1 minus 1 plus I to the power of negative n. And the same formula for Glenda. Nothing changed. Both same formula. So it's the same. What we're doing a comparison. So when you do a comparison, we're going to be using the same formulas. So formulas, next part is the substitutions. And again, when we do the substitutions, we're going to leave the I value as a fraction. So you're going to see we have fractions on top of the big line, fractions underneath of the big line. So there's a lot of things going on here. So it's one of those where we have to be careful. So let's do the substitutions. So the present value, and again, it's important. I find it easier if I write down my givens first up here. If I write my givens down, then I just get to pick them out from here, put them into the formula, instead of having to go up here and try to find them in the paragraph that's written there. Okay, so it's easier to do it this way, write down the givens. The present value is 14,000 for both of them, but the interest rate is different. I for Brett is 0.085 divided by 12. And for Glenda, it's 0.121 divided by 12. And underneath, we have 1 minus 1 plus I to the power of negative n. So it's going to be 1 minus 1 plus 0.085 divided by 12, all to the power of negative 48 for Brett. And for Glenn, it's going to be 1 minus 1 plus 0.121 divided by 12 to the power of negative 48. So these are going to be tricky. Mostly, right now all we've done is we've wrote the formula down and we've done the substitutions. Now it's the calculator is going to be the tricky part. Or we're going to get this right using the calculator. So remember that when we have a fraction where we have the big line, so everything on the top is divided by everything on the bottom. So it's like everything at the top is inside of a bracket, everything at the bottom is inside of a separate bracket. And then we're divide is the last step. So there's a couple of ways of doing this. If you do it, if you think about everything on top in a bracket, everything on the bottom in the bracket, we can do it this way. So what I'm going to do, I'm going to go fairly slow. I'm going to go bracket. Now the bracket is not on the screen though. I'm just putting it there to make sure that I do the calculations correct. So bracket, then I got a bracket 14,000. So I can put another bracket, 14,000 bracket. Oops. And then another bracket is going to be 0.085 divided by 12. Close that bracket. Then I got to close the top bracket. And then I'm going to divide by, we put a bracket, 1 minus bracket, 1 plus 0.085 divided by 12. Close that bracket to the power negative 48, and then close the other bracket, and then press enter. And I get 345.076247. Round that to the nearest penny, and I get $345.08. So I'm pretty sure, actually I'm positive that my calculations are correct, because the number that is on screen in red as the answer is the same number that I got when I did the calculations. So my math on using the calculator is correct. So if you got the number 345.08 using whichever method you use, and again, it depends on the calculator you're using. So the important part, if you show me what you're given for each of the two individuals, what was given for each one, and then you write the formula down for each one, do all the substitutions for each one, and then you make a mistake and you get the wrong answer. But so 1, 2, 3, 4, 5, 6, 7, and then 8, 9, 10. So I would probably have this marked out of 20. And if you get the wrong answer, you'd get 18 out of 20, 90%. So if you show all of the work, make one little mistake, you're not going to lose many marks. But if you don't show any of the work, don't do any of this right here, what I did, and you get the wrong answer, then I don't know how you got your answer. And if I don't know how you got your answer, I can't give you any marks. Okay? So let's finish Brett off, and then we'll go work on Glenda after. So Brett's going to pay $345.08 per month, and it's for 4 years. So 4 times 12 is 48. So it's going to make 48 payments. So 345.08 times 48 is 16,563.84. So the total interest is going to be this amount, the total payment, minus the present value of 14,000, which is $2,563.84. And then so that is as far as we can go for now. So Brett's going to pay total interest of $2,563.84. Just hide that for now. So now let's do Glenda. So same thing. There's the formula. Due to substitution, the present value is up here of 14,000. So that's where that 14,000 comes from. I is right here, 0.121 divided by 12. There's my I value right here, 0.121 divided by 12. Divided by 1 minus 1 plus I is right there again, 0.121 divided by 12 to the power of negative n is 48. So I'm going to do the math again just to double check to make sure that I did it correctly. So bracket, 14,000, close that bracket, open the next bracket, 0.121, divide that by 12, close the two brackets on the top now, divided by another bracket, 1 minus bracket 1 1 plus 0.121 divided by 12. Close that bracket, and that's to the power negative 48, and then close that bracket. Press equals, and I get 369.3614597. So rounded that to the nearest penny is 369.36. So the total payments is going to be 369.36 times 48, because there's 48 payments, 4 years, monthly payments. It's going to be 48. If you go 369.36 times 48, you get 17,229.28. And if I subtract the 14,000 that we borrowed, then the total interest is going to be $3,729.28. So now you can see that Glenn paid more interest than Brett did. So the difference between the two is going to be 3,729.28 minus 256384, which is a total of $1,882.44. So based on this, 4 years, $14,000, Glenda is going to pay $1,182.44 more in interest than Brett. So you can see that the interest rate, 4%, nearly 4%, can make a big difference over a 4-year period, how much more you're going to have to pay. Look at the monthly payments, 345, 369, so what, 20, close to $25 a month. Doesn't sound like a lot, but over 4 years adds up. Okay, so that is a problem that involves calculations and using the present value formula. Or sorry, this one involves the monthly payments. Okay, so we're going to move on from there. And the next part of this, there's some support questions that are similar to the ones that we just did. Very similar, actually. So if you can follow what we did on the screen here, then you shouldn't have any issue with the problems coming up. These support questions shouldn't be that big a deal for you now. So you just need to read each of the questions and then write down what you're given, and then go back up to the 3 examples. So 9.1, 9.2, 9.3 sample problems, and see which one is similar to which one of these, and then use it to help you solve that problem. So we were talking about loans. So when you get a loan, you have to pay it back, making monthly. They call it sometimes called installments, monthly installments, monthly payments. RRSPs. So an RRSP stands for Registered Retirement Savings Plan. So typically when you start work when you're young, you put some money away so when you retire, you have some money to live on. And that's where a registered retirement savings plan comes in. So typically what happens, maybe when you get a job, your employer will take a certain amount of money and put in an account for you that you don't have any access to. You can't touch it until you retire. So it's a savings plan. Sometimes you can get them at banks if your employer doesn't have one, but typically most employers will have some sort of a retirement savings plan system that you can access. So again, it's money you save for retirement. So it's when you start putting money in, you're not taking anything out until you turn a certain age, 60, 65, depends on what age you retire at. Once you retire, then you can start collecting money. So up until the point you retire, you're putting money in. So every month you're making a monthly payment, payment, payment every month. And then at the end, when you retire, you stop making monthly payments. You don't make any of those anymore. Now you start taking money out. So you pay money in, and then later you take it back out. Okay. And the idea too is when you retire, you probably have less debt. So you probably don't owe as much money, and you're not going to need as much money to survive or to live on. So you don't need as much. So you can take less out than you put in, and then pay less tax on if you have to pay income tax on it. Okay. So that's an RRSP. Now, there are four formulas on the next page here. I'm just going to highlight them for you. Highlight them in yellow. Some of them are similar to what we've seen before, but they're going to be slightly different. Uh, we've done the R value here, and we've done the PV. So if you come back up here, PV equals 1 minus 1 plus I to the negative n over I. Okay, PV equals R times 1 minus 1 plus I to the negative n over I. Okay, so those formulas, we've worked with those two down here already. These two are going to be new. So if you plan to contribute to an RRSP, we're going to use these formulas right here. If we want the present value of annuity and how much we need to put in now to have a certain amount of money in the future, we're going to be looking at these formulas down here. Okay, so there's a couple of examples done in the material that you would have received. I'm going to leave those to you, and then I'm going to work out some other examples so you have some extra work to look at. Okay. So sample problem number 9.3. Is that going to be 9.3? It should be 9.4. Let's come back up here now. I thought this one, yeah, that's 9.3 there. So it's actually going to be 9.4. Okay. So let's look at a problem that's similar to the one that was up above. Chastity began making monthly contributions to her RRSP at the age of 22. Her monthly contribution starting 1 month after her 22nd birthday was $140. And her RRSP earned interest at an average rate of 6.75% compounded monthly. Chastity stopped making contributions when she retired at the age of 60 and started to withdraw a pension from her RRSP. So we're going to break this problem down into steps and lay it out step by step so we don't make any mistakes. So first of all, we need to figure out how many years the money was invested for. So 22nd birthday, she retires when she was 60. So 60 minus 22 is 38 years. So she was making payments for 38 years. And she was making monthly contributions. Okay. Monthly contributions, $140 per month. And it's 6.5% per year compounded monthly. So that is the information that we're given. So we know what the monthly payments are. It's $140 per month. We know that the end value is 38. So 38 years times 12. So it should be 456 payments. We know that the interest rate is 6.75% or 0.0675. Divide that by 12, and I get I equals 0.005625. So what I'm looking for is the amount. So how much money will be there in 38 years. So that formula is, again, up here. I'm looking for the amount. So I'm going to be using this formula right there. A equals R times 1 plus I to the power n minus 1 over I. Okay, so that's the formula. Again, so the first step, same procedure every time, is to, I'll just tab over here, formula. First step. Second step, as always going to be the same steps, substitutions. And then calculations and rounding. Calculations and rounding. Okay. We don't need any of that bolded. Okay. So the formula is the amount is what I'm looking for. And this is the formula for the amount equals R, which is the monthly payments, times 1 plus I to the power n minus 1 all divided by I. Now this one's going to be a little bit easier. So I'll do the substitution. R is 140 times 1 plus 0.005625. And because the fraction gave me a nice number, I didn't have any, it wasn't like a really long number that was rounded up. I can use that number instead of the fraction. So now it's going to be a matter of doing the substitutions. We've done those. Now it's going to be the calculation. So let's do that on the calculator. So we could probably do it this one a little bit differently. So I'm going to do what's inside the bracket first. So what's inside the inside bracket at the top first. 1.005625 to the power of 456 payments. And then I'm going to times that by 140. Then I'm going to subtract 1. Then I'm going to divide that by 0.005625. And I'll get 321,076.9494. So round that to the nearest penny is 321,076.95. So after 38 years of putting in $140 a month, you'd have over $321,000. Okay, that's not bad. The next part, she decides to reinvest the total amount of her RSP to provide an annuity for her monthly income during her retirement. Suppose Chastity was able to obtain the same average interest rate, so 6.75%, and chose a 25-year term for her annuity. What monthly pension could she withdraw for the next 25 years? So again, write down what you know. This time the present value, we know because we've retired, or she has retired. So she now has $321,000 in the bank. She wants to take out monthly payments for 25 years. So she's 60 now, so that'll be 85. The interest rate is going to be the same. Divide it by 12. It's going to give you 0.005625. So now the monthly payments is going to be R equals PV times I over 1 minus 1 plus I to the power negative n. Do the substitutions again, just like we did up here. formula, substitutions, calculations. So the present value is 321,076.95 times 0.005625. 1 minus 1 plus 0.005625 to the power of negative 300. Okay, so I'm going to do everything on the top separate from everything on the bottom. I'm separate, put in brackets. So bracket 321 076.95 times 0.005625. Divide that by bracket, just like you see there, 1 minus bracket 1 plus 0.005625, close the bracket, to the power negative 300, and then close the bracket, press enter. I made a mistake somewhere. So I'm going to clear that. Let's go do it all again. So bracket 321 076.95 times 0.005625. That's the top part. I'm going to divide that by everything that's on the bottom. Bracket 1 minus bracket 1 plus 0.005625. Close the bracket to the power negative 300. Close the bracket. Now I got it. So 2218.3576. So if I round that to the nearest penny, it's going to be $2,218.36. So that's how much she can take out per month upon retirement. So for the 38 years that she was working and putting money into the account, she was only putting in $140 per month. Okay, so not a lot of money, but when she retires and she's going to take money out, she can actually take out over $2,000, so $2,218.36. So you can see the benefit of saving money, starting early in life. So the earlier you start, the more interest you will earn. So you, like I said, a small amount per month will go a long way when you retire. And so $140 a month is not a lot, but $2,218.36 a month is quite a bit of money. So that is how you would solve those sorts of problems. So again, each of these problems will help you with the support questions and the key questions in lesson number, I think we're in lesson number 9 still. Yeah. Okay. So now you have enough, I think you do, to help you complete the rest of the support questions. And then if you do the support questions, you should have no issue with the key questions. So I'm going to get you started on a couple of the support questions. And again, the first thing you need to do is, what are you given? So start there. Okay. Always start with given. And again, it's easier to do it this way than try to, when you're trying to plug numbers into the formula, than to go back up and try to find them in the paragraph that's written, because there's a lot of words there. So Mary is converting her RRSP into an income fund. She wishes to receive $1,500 every 6 months for the next 20 years. She is guaranteed an interest rate of 6.25% compounded semi-annually. How much must Mary deposit now to pay for the annuity? So what are we given here? Okay, so we know that it's going to be, she wishes to receive $1,500 every 6 months for the next 20 years. She's guaranteed an interest rate of 6.25%, and that should be per year. Okay. Compound is semi-annually. Semi-annually means twice per year. Or so yeah, twice per year. How much must Mary deposit now to pay for the annuity? So uh, she wishes to receive $1,500 every 6 months for 20 years. So that means twice per year. So if we look at, well, that we can do the n number, we can do the n value first, right? So let's do it this way. Insert formula. And we can move things around after. We don't need it to be underlined. So n is equal to, so she wants twice per year for 20 years. So come up here times 20. I'm going to put this on the left-hand side over here. And then we can say that, make a copy of that. Put down here. So, and 2 times 20 is going to be 40. And then here, the R value is, oops, get out of here. The R value is going to be how much we're making payments for. So the R value is going to be 1,500. 6 months. She wants to receive $1,500 every 6 months for the next 20 years. Okay, so we get the R value. She's guaranteed an interest rate. So I, so I value is going to be, so 6.25% as a decimal is going to be 0.0625. And I need to make that a fraction because I need to divide that by 2. And if I do that, what do I get? Oops. Let's make a copy of that. Put it out here. So my I value is going to be, calculator, see if we get a nice even number, 0.0625. Divided that by 2 because it's compounded semi-annually. Divide that by 2, and I'll get 0.03125. 0.0625 divided by 2 is 0.0, so 3.125%. Okay, so there's my n value. There's my R value, and there's my I value. So the question says, how much must Mary deposit now for the annuity? So now, if you we need the present value formula because we're asked for present value. What you need to invest now? So the present value formula is that one there. So I'll come back up here so I can find, oh, it's not there, back up here. Present value. Okay, we'll get there eventually. So this formula right here. So my solution, I'm going to make a copy of that so I can come down here. I'm not going to work through all of this with you because this is a support question. You can work through that. So now there is the solution will be to plug those values, your R value, your I value, and your N value into your calculator. So there's the formula. Do the substitution, then do the calculations. And if I'm not mistaken, if you scroll to the end of the come down here, you'll see you'll get the answer. So 6, 7, uh, lesson number 9 is right here. So you can find the now for some reason here it doesn't come out too well, the formulas. So but you can see what the answer is at least. So once you plug the values in, okay, you can do the calculations and see if you get that number right there. $33,982.11. Okay, so again, support questions is best to work through them on your own, and then after you've done them, see if you get the same answer that is in the back where the answers are. Okay, so I'm just going to scroll back up here, lesson number 9. So some of these you may have to reread the question several times as well before you understand what you have to do. But if you break it down like I did here into what's given, okay, you will have, so if you do this part like I did here, N, R, and I, you should have less of an issue with solving the problem. So it's important to do it step by step. So let's start the next one. What are we given? Okay, so we'll put that here. So Josh is 27 years old and wants to start putting money into an RSP on a bi-weekly basis. That means every 2 weeks. If he wants to have $1 million by his 65th birthday, how much should he deposit regularly if he can earn an average interest rate of 6.75% compounded bi-weekly? Does this seem reasonable? And then justify your answer. So it's a little bit more. So what do we know? Well, we need to figure out. So just like the one that we did, I'll just come up here a little bit now so I can, because we're talking about here. Remember? So 22nd birthday, retiring at age 60. So this is that's what I mean. So when you're doing these support questions, if you look back up, find an example. Uh, so it might, this one is slightly different though, because now it says, this one says, uh, If he wants to have $1 million by 65th birthday, how much should he deposit regularly? So number of years of investment, your number of years of deposits. Okay, so we're just going to change it slightly, but it's a little different, but similar. So 65th birthday, and right now 27 years old. So 65 minus 27, let's do the math. So 65 minus 27 is same number, 38. So 38 years. Okay, so that we know is 38 years. So now I can calculate my N value. Okay, so here my N value is going to be, so invest the money for 38 years, and it's going to be making payments every 2 weeks. So there's 26 weeks in a year. 26 times 2 is 52. So it'd be 52 payments per year. So 52 times 38 is going to be 1,976 payments. 1,976 payments. Oops. 1,976 payments. Got that. Now we can do the calculation for the interest rate. Okay, down here. So the interest rate again, this time is 6.75%. And this one we're probably going to have to leave as a fraction because it's 6.75% per year. Oops. Compounded biweekly, so it's going to be 6.75%. Divide that by 52. Now, if you do that, do the math. So if you do 0.0675, divide that by 52, you'll get 0.032096838. So that's a little bit too long and it's probably rounded off. So let's leave it, this case here, we're going to leave I as a fraction. And we were asked to find, so we know that the future value, the amount in the future, A, oops, let's do this, get rid of that. And here, A is going to be 1 million. And what we're asked to find is the R value. So how much should you deposit on a regular basis? Okay, so the R value, so we come back up, right up over here. So the R value is going to be, actually, no, we're going to use a different formula now. So we have to use, because we're talking about the amount now, not the present value. So R is going to be, we have to use this formula right there. Come down here. So now we have to use, oops, it's gone down here, but next page. So we don't need it highlighted anymore, and we're going to change it to red. And I'm going to move it back up here. Oops. Doesn't want to go over there. Okay. Move it down again. Okay. Let's come back up here. Let's see if I can make some room to get it up there. I don't know what happened to it there. But anyway, that's the formula you would use to solve that problem. That's as much time as we have for today. We'll fix this up next week when we come back on Monday. Thank you for participating, and I look forward to talking to you next week. Bye for now.